So we've all been there. You're using an AI, maybe it's ChatGPT, maybe it's Gemini or Grok from Elon Musk's XAI. You ask it a question, and it gives you this super confident, super detailed answer. It sounds completely legit, but then you check and realize it just made it up. This is what we call an AI hallucination, and it's one of the most frustrating problems holding AI back. It's a huge deal for OpenAI, Google, Microsoft, leaders like Sam Altman and Satya Nadella, because when an AI invents facts, it breaks our trust. Before we dive into the solution, it's crucial to understand why this problem is so deeply embedded in the first place. Fixing AI hallucinations isn't just about squashing a few bugs. It's about confronting the very nature of how these models are built and the psychological traps they set for us. At their core, models like GPT-4 are designed to be helpful, fluent, and authoritative. This is a feature, not a bug. They are optimized to generate text that is grammatically perfect, contextually relevant, and above all, confident. When they answer, our natural human bias is to believe them. We're wired to trust a confident source. They don't hedge or express doubt. They state outputs as facts. This is partly because accurately estimating their own uncertainty on a given statement is still a massive technical challenge. So unless you're already an expert in the topic you're asking about, their fabrications are incredibly tough to catch. For years, two major theories dominated the discussion about why this happens. The first theory points to the data itself. The internet is messy. It's filled with conflicts, biases, and outright falsehoods. During training, facts that appear frequently are learned strongly and reliably. But rare, obscure, or nuanced facts are learned weakly. When asked about them, the model's internal representation is faint, so it essentially guesses to fill in the gaps, prioritizing a plausible-sounding answer over the fragile truth. The second theory focuses on the training process, which rewards fluency, not necessarily truth. There's a critical difference between training for coherence versus calibrating for truth. The reinforcement learning and fine-tuning stages often punish an honest, "I don't know," because human raters prefer a helpful attempt over a refusal. So, the model learns it's better to fake it convincingly than to admit ignorance. But those are big-picture stories. They tell us it happens, but not. What is physically happening inside the vast network of artificial neurons when it decides to lie? That's the microscopic question the team at Tsinghua University set out to find. So, how do you find a single lying neuron in a digital brain containing billions, or even trillions of them? It's a search for a needle in a haystack the size of a continent. The researchers started with a powerful hypothesis, that hallucinations aren't a system-wide failure. Instead, they suspected that only a tiny, specialized subset of neurons was responsible for derailing the model's output. They gave these theoretical culprits a name, H neurons, short for hallucination-associated neurons. The mission was clear. First, prove these H neurons actually exist, and second, develop a method to pinpoint exactly which ones they are, neuron by neuron. But this is incredibly difficult. The internal state of a large language model is a storm of activity, a constant, noisy chatter of calculations. Simply looking for the most active, or loudest, neurons is a trap. Think of it like a boardroom meeting. One person might be shouting, dominating the conversation, but their volume doesn't mean they have the most influence. The real decision might be swayed by a quiet expert in the corner who makes one critical, perfectly timed point. In a neural network, the loudest voice isn't necessarily the decider. To find that quiet expert, the team developed a new tool. They called it CETT, which stands for Causal Efficacy via Token-Wise Tracking. It's a metric designed to measure true influence, not just noise. CETT works by meticulously tracking how much the activation of a single neuron directly caused the model to choose its very next word, or token. It quantifies the precise causal link between a neuron firing and the final output. This method effectively cuts through the background chatter, ignoring the loud but irrelevant neurons and revealing the true influencers, the ones that actually steer the ship. With SET, they could finally trace a specific hallucinated word, that one wrong fact, all the way back to the individual neurons that caused it. The strategy was simple yet brilliant. Compare the model's internal state during truthful moments against its state during false moments. By doing this repeatedly, they could see which neurons consistently showed up with high causal efficacy every single time the model lied. This wasn't just about finding a correlation, it was a careful, microscopic hunt for the direct cause. To find the source of a lie, you need a brilliant trap. And the setup here was every bit as clever as the idea itself. First, they took a massive, reliable dataset, Trivia QA, which is packed with general knowledge questions that have definitive answers. They then asked the AI model each question not just once, but 10 separate times. This repetition is crucial for establishing a pattern of behavior. Is the model consistently right, consistently wrong, or just randomly guessing? To make things even more interesting, they cranked the model's temperature setting all the way up to 1. Think of temperature as a creativity dial. At 0, the model is deterministic, always picking the most probable next word. At 1, it's at maximum randomness, exploring a much wider, more unpredictable range of possible answers. This combination of repetition and high temperature is a powerful stress test. It forces the model out of its comfort zone and reveals what it truly knows versus what it's just confidently guessing. After running this experiment, they filtered the results down to the extremes, a set of 1,000 answers that were always correct and another 1,000 that were always wrong. Now for the most ingenious part. They didn't just look at the wrong answers, they pinpointed the wrong word, the single token that flipped the statement from truth to falsehood. A separate, simpler model was used to precisely mark this hallucinated word. This avoids confusion, ensuring they weren't just tracking neurons responsible for grammar or sentence structure, but the specific neurons that produced the lie itself. With the target identified, they used CETT to measure which neurons were most influential in generating that specific, incorrect word. Finally, a transparent linear detector sifted through that data to identify the top predictors. The result was astounding. They found a tiny, consistent set of neurons that reliably activated when the model was hallucinating. They called them H neurons. And this wasn't a fluke in one system. Across vastly different models from GPT to Gemini to Grok, this microscopic signal, this neural signature of a lie, kept appearing. The results were mind-blowing. H neurons were shockingly few. These models are massive, yet less than 1 in 100,000 neurons tied to hallucinations. Mistral 7b showed 0.35 ppt. Bigger models, even smaller shares. Hallucinations look localized, a tiny faulty circuit. The same H neurons fired across normal, biomedical, even made-up questions. When honest, H neurons stayed quiet. When lying, the same tiny cluster spiked. This pointed to a behavior, over-agreeing, not a broken memory. For Anthropic, OpenAI, Microsoft, NVIDIA, if behavior is the root, alignment must target this circuit. Next, prove causation with perturbation experiments. Turn the dial up. See if behavior shifts. With the dial low, it says cats have fur. Dial high, and it agrees, confidently wrong. Low dial, physicist and chemist. High dial, it complies with the fake context. Low dial, it stands its ground. High dial, it flips to appease you. Low dial, refuses, safety holds. High dial, guardrails give, it complies unsafely. Conclusion: turning up H neurons causes overcompliance, the behavioral engine of hallucinations. Across all trials, the pattern is clear. Cranking H neurons didn't erase knowledge. It just made the model a people pleaser. So we need behavioral fixes. Can we delete H neurons? Not safely. They're tangled with natural fluency. Crushing them makes answers robotic and less helpful. We need balance, truthful yet fluent. One path, a real-time detector watching H neuron spikes. If it spikes, flag and prompt a double check. Another, training to dampen H neurons without hurting language. For OpenAI, Google, XAI, Anthropic, NVIDIA, Microsoft, this is a playbook.